Hi everyone. So today we are going to start a very exciting topic which is eigenvalues and eigenvectors. This topic is very nice, quite important for interviews and as well as for GATE. So let's just see that what are these eigenvalues and eigenvectors. And this is going to be a very exciting topic. So see, we have seen rank, that was just one way to look at the matrix. But eigenvalues are the new way to look at the same matrix. So basically, this rank is one number which is so powerful that a number can have. I mean, just a one number that it doesn't matter that whether your matrix is 500 into 500 dimension or whatever dimension you have. But this number itself is telling you very meaningful information about even a very big matrix. Similarly, the eigenvalues are just another numbers which also tell you very powerful information about the matrix. So rank was just one way to look at the matrix. Now we have the eigenvalues, which is a new way to look at the same matrix. Okay, cool. Now in this chapter, as I told you, in this chapter in the determinant also I told you that we only have the square matrices. So let me write here that in this chapter we only have square matrices. So what do I mean by square matrices? It means that number of rows and number of columns are same. Okay, this is what I mean by square matrices. So in this chapter we will be having all the matrices as square matrices. Why? Because eigenvalues and eigenvectors are defined for that. So I will tell you this like in couple of slides. Okay, cool. Let's start with a very nice question, which is that what happens when a matrix hits a vector? Which means that you have a matrix and you have a vector. If you multiply a matrix and a vector, then what's going to happen? We have already seen this couple of times that this is the linear combination of columns of A, right? But the eigenvalues, as I told you, is just another way to look at matrix and vector multiplication. I can say it is one of the special example of matrix and vector. Okay, so matrix and vector multiplication we have already seen in Ax equal to B. I mean that was the whole topic. So here also we will see the matrix and vector multiplication, but for the special for the special vectors, for a given matrix, there will be a special vector that I will be multiplying, that is called eigenvector. So let's just see in general also that what happens geometrically if you multiply a matrix and a vector, then geometrically what's going to happen. Okay, let's just see. So suppose that you have a vector which is, let's suppose x. This could be anything, could be let's suppose 1 2. Now you multiply this vector by a, and let's take a matrix A to be, like I'm taking a random matrix, maybe 0 1 0 1 1 1, some matrix. Okay, some random matrix I'm taking, and then you multiply this matrix which is 0 1 1 1 by x, which is 1 2. Then let's just see what you are getting. 1 times this and 2 times this, which means 2, and then this will be 3, right? So you will be getting 2 3. So which means it was 1 2, let's suppose, and then you got 2 3, maybe somewhere here, right? Maybe somewhere here. So what do I mean by that? This is basically Ax, which is 2 3, right? So you started with 1 2, but because of this matrix multiplication, you converted that 1 2 to 2 3. So this is what matrix multiplication is doing geometrically, isn't it? So you can say that if you're multiplying a matrix with a vector, so vector is looking like this. When you multiply a matrix or a vector, that is also a vector. Ultimately, this is also a vector. But the new vector or the resultant vector is basically some vector that is getting rotated, right? That is getting rotated and maybe scaled also, which means like it is getting shrink, or it is getting scaled or something like that, right? I mean stretch or shrink, any sort of things can happen, depends on the matrix actually. Maybe the values are maybe too less, maybe in that case I don't know, maybe the vector will be shrink, right? Anyway, what do I mean geometrically is that here you have a vector x, but the ultimate vector that you got Ax is some, I mean this Ax is some vector which is basically different from x, which means that this Ax is having some other direction. But that is just one possibility, which means that there is one possibility that you have a matrix and you have a vector. You multiply this matrix and a vector, you get Ax, and then Ax is some other vector, which means the vector get transformed into a new vector. Okay, so this is just one possibility, but there could be another possibility also. So what do I mean by that? See, you have a vector, you multiply a matrix with the vector. Do you always get a new vector, or maybe you get the same vector, right? If the matrix is identity matrix, then you may get the same vector, or maybe you get the vector which is in the same direction also, right? So basically, let's see that as a possibility too, that the vector get scaled, which means that you have a vector x, and now you multiply that by a. Now whatever Ax you have, in this case, particularly in this case 1 2 2 1, if I take the specific example of this matrix, a specific vector, then Ax is coming out to be 3 into 1 1, which is actually 3x. I mean, the Ax that you calculated, right, that turns out to be 3x, which means that this x and Ax, or the 3x, because Ax is just 3x, are having the same direction. See, earlier they were not having the same direction, but now they are having the same direction. So there are two possibilities. First possibility is saying that you multiply a vector with the matrix that get rotated. This is the first possibility. Another possibility is that need not to be rotated. That could be in the same direction also, right? So you multiply a matrix with a vector. If that is in the same direction, that kind of vector is called eigenvector for that particular matrix A. So here x is eigenvector. So which means that for this matrix A, the vectors which have the same direction after the multiplications are called eigenvector. Okay, so let me define it mathematically, that you multiply a vector, you multiply a matrix with a vector Ax, and then ultimately you get same x with some constant difference. Okay, maybe lambda. So lambda is one scalar here. Now this x you multiply with a, you get lambda x, 2x, 3x, maybe 1 by 2x, 1 by 3x, something like this, right? Then this vector x is called eigenvector of A. Eigenvector of A. Okay, that is called eigenvector of A. I hope you understood. Now for example, you multiply, let's suppose the earlier matrix. Okay, I mean, let's suppose you multiply this any random matrix A with x. Let's suppose you get 3. Okay, I mean 3x. Then this x is eigenvector. Suppose you multiply A with x, then let's suppose you get 0.5x. Then this x is eigenvector. So basically you multiply a matrix and a vector. If you get the same vector, okay, the constant could be 1, could be, I mean, it could also be the case that you get the same vector. If you get the same vector with the constant difference only, then that vector is called eigenvector for that matrix. Okay, so like geometrically, actually these kind of things are little important in the interview, because they will they will be asking the geometric interpretation. And how do I know that they will be asking or they will not be asking? Because I have that experience. Like I have been to ISC, and this is how I mean the professors teach at ISC. So I remember the first class of machine learning. Obviously they won't explain that much. They will just go through the slide like this. Okay, this is first possibility, this is the second possibility, and then that's all. I mean, they won't explain that much, but yeah, they have these kind of things in the slide. So if the professors have these kind of things in the slide, then they have in their mind also, and if they have in their mind, then they will ask in the interview. So that's the human nature, right? Okay, so I hope you understood that what is the geometric interpretation of eigenvector, why that is so important. I will come to that, don't worry about it. I will come to that. Okay, so there are two possibilities. One is that you multiply this W by a matrix A, you get another vector, or you get the same vector with the scaled version. Now, suppose you multiply A with X, you get lambda X, right? Now, in this case, it will depend whether you are going to stretch it, you are going to shrink it, or what's going to happen. I mean, it will depend on the lambda. So, if lambda is let's suppose 1, then in that case, you are going to say that no change. If lambda is greater than 1, you will say it got stretched, right? If lambda is less than 1, you will say maybe it got shrunk, something like this, right? So you can have these possibilities. I mean, if the earlier vector is like this, and then if lambda is less than 1, then maybe ax is just like this, right? It might get shrunk. Lambda could be 0 also, it's not an issue, right? Lambda could be 0 also. If lambda equal to 0, I mean this is a special case here, then also it is shrunk, like you just shrunk down to 0. Lambda could be 0 also. Eigenvalues could be 0 also, it's not an issue. Okay, so let's come to very important point, which is that why these are in limelight. Why these are so popular? I mean, everyone is talking about eigenvalues, eigenvector, and everyone is interested in knowing that. Why are they always in limelight? It turns out that there are several properties of matrices can be analyzed based on their eigenvalues. Actually, at this point in time, I cannot go in the detail, but I can tell you something, okay, which you might find later useful. In machine learning, there is something called regularization. Okay, maybe regularization. So in regularization, there's a concept that, I mean, in regularization itself is a concept. So regularization is actually a concept which is getting used in almost every machine learning algorithm. I mean, like you cannot even imagine any machine learning algorithm without regularization. Otherwise, like model will either underfit or overfit. Okay, so basically this regularization is very important concept of machine learning. I can say that machine learning, in like the total of machine learning or the deep learning or whatever we see today, cannot even exist without regularization. And you know what, this regularization base, the core concept of the regularization is eigenvalues and eigenvectors. Okay, so I can say that machine learning cannot survive without it, and core concept of regularization, core concept, I mean if you go to mathematical concept, okay, regularization, if you talk about the mathematical concept, then the core concept of regularization is eigenvalues and eigenvectors. So that much important this eigenvalues and eigenvectors are. You can see that transitivity, right? I mean, machine learning is depending on regularization, and regularization is depending on eigenvectors and eigenvalues. So that much important this eigenvalues and eigenvectors are in machine learning. Now there are many applications, like I mean apart from the regularization also, like there is one application called principal component analysis, that extremely popular application that is based on the eigenvectors only. I mean there are something called principal components, and that are the eigenvectors of some matrix. So anyway, like there are many important applications also apart from the regularization. So that is why this eigenvalues and eigenvectors are very popular and very much needed in machine learning. Okay, cool. Now let's have one diagram. Here I just draw one axis, and like the same axis I have drawn here also. Now what I want to do, I want to take a vector or take a point from here, and I want to multiply that point to this particular matrix. Okay, so suppose I take xy, if I multiply to this particular matrix, I will be getting this. I think I have the examples on the next page. Yeah, so if I let's suppose take this point, which is 0 0. If I multiply 0 0 with this matrix, then you will be getting 0 0. If I multiply 1 0 1 0, this particular point, then you're getting 9 4. I think this one. If I multiply 0 1, you get 4 3. X value 0 and y value 1, right? Then you get 4 3. If I multiply minus 1 0, if I multiply minus 1 0, yeah, x value minus 1 by y value 0, then you get minus 9 minus 4. I think this one, something like this. So basically every point is getting here and there, right? I mean if you multiply some points with the matrix, obviously they will get here and there, right? You multiply, like this 0 is here only, this one is here, this one okay, not this one, sorry. So basically this is 1 0 1 0 is 9 4, 1 0 is 9, this one is here, and like that, right? We can map it. So basically every point is getting here and there. Now I think just to draw, I can connect all these points which is in the circle. I can connect all of these points which is in the ellipse. Now instead of point, if you want, I can talk about the vectors also. See, this was one vector. This vector now get changed if you multiply by the a, it get changed to this vector. So this was x, which used to be 1 0, but now it is 9 4, right? Now it is 9 4, which is AX. Okay, that's fine. But I'm not interested in those random vectors. I'm interested in the eigenvectors only. So now you just see those two special vectors here, which are actually axis of this ellipse. Okay, if you just see this axis of this ellipse, this vector earlier was this one, which used to be 2 1. Okay, so this is 2 1. If you multiply 2 1 by that, then you are getting 22 11, which means if you multiply this 2 1 by this matrix, then you are getting 22 11, which means 11 into 2 1, 11 into 2 1, which means what I mean to say is that there is one vector which is 2 1. If you multiply that with the matrix A, you are getting the same vector. I mean, same vector in the sense that you are getting the vector in the same direction, and the constant is some different, right? Similarly, there is another vector which is on the minor axis of this this ellipse, which is actually this minus 1 2. Okay, that vector was earlier minus 1 2, and now also it is minus 1 2. I mean, doesn't matter, the constant is 1. So basically there are two vectors on these axes, right? There are two vectors. One is this, one is this. Those vectors are not getting changed in their direction. Earlier whatever was the direction, now also the same direction. Okay, so see, all other vectors are getting changed. It is just the two vectors are not getting changed, and those two vectors are called eigenvectors, right? So this matrix has two eigenvectors, and that is why that apart from these two vectors, all the vectors, which means like this vector is getting changed to this vector, like that, right? So this vector is 1 0, now getting changed to this 9 4 or something. So apart from these two vectors, every other vector is getting changed, and these two vectors are called eigenvectors. I hope you understood. Cool. These things are little I mean advanced in the sense that I'm just talking about some geometric sense, but I will not talk about the linear transformation and all, and change of basis, linear transformation, eigenbasis, and these things are little advanced, but you don't need it, right? I mean, you will be needing it at masters. Okay, when you go to top IIT or IIC, then only you will be needing it, and then also like if you choose to pursue your MTech in mathematics or machine learning. Okay, cool. So now let's just formally define this eigenvalues and eigenvectors. If a vector v can be multiplied by a such that the final result is lambda v, then in that case you say that this v is eigenvector and lambda is eigenvalue. Okay, I hope that is clear to everyone. Now interestingly, this lambda can be 0, also. And since like this vector v, the eigenvector, the core idea of the eigenvector that it doesn't change the direction, right? Since like we want that kind of interpretation of this eigenvector, that is why by definition I'm saying, okay, there is no reason actually about it, but by definition I'm saying that eigenvectors are non-zero. Okay, it is not like that there is some reason behind it. It is by definition that I do not have zeros as eigenvectors. Reason is simple, because we want eigenvectors to be something that has the same direction after the multiplication. Maybe get shrink, maybe get elongated, or maybe get stretched. That is okay, but we want the same direction. But if you talk about zero vector, it is actually not having any direction. Zero vectors doesn't have any direction, so it doesn't give you the geometric meaning, and this might be one reason. Another reason could be like if you have zero vector, then like I mean, what will be the eigenvalue? Like you will be getting the same vector always, right? And then eigenvalues could be anything here. So this is also little not nice convention to define. So because here the eigenvalues could be anything. So that's why like people just avoid the zero vectors, and they say that okay, zero vectors cannot be the eigenvectors. Okay, this is by definition. But the eigenvalues could be zero. Okay, so eigenvectors has to be non-zero, but eigenvalues could be zero. So let me write it here. Eigenvalues could be zero. Eigenvectors cannot be zero by definition. Okay, eigenvectors cannot be 0, and that is by definition. Okay, I hope you understood. Cool. Now there is one side note, which is that eigenvectors only make sense for the square matrices, which means if I want the same vector, and let's suppose this is not a square matrix, it is m cross n, and this has to be n cross 1 because of the dimension match, right? Then ultimately you will be getting something of m cross 1, and then I cannot even get the same vector. Since I want the same vector, then it doesn't make any sense that eigenvector can be defined for rectangle matrix also. It will always be defined for square matrices, right? I mean, this is just a side note. I hope you understood. Now, let's just take one example. Suppose you have one matrix which is called identity matrix, which looks like this: 1 0 0 0 1 0 0 0 1. And if you multiply any vector here, let's suppose I multiply any vector x, which is, let's suppose, 1 2 3. Okay, so I multiply in this matrix 1 0 0 0 1 0 0 0 1. I multiply a vector which is 1 2 3. Then what do you get finally? You get 1 2 3 only, right? Because it's the identity matrix. Okay, now it seems like that 1 2 3 is an eigenvector, isn't it? It seems like 1 2 3 is an eigenvector. Let me know if there is any problem here. Because you multiply x, you get the same x. And what is the eigenvalue? Eigenvalue is 1. Because 1 into that. Now, you take this identity matrix, which is 1 0 0 0 1 0 0 0 1. You multiply some other vector of your choice, maybe 2 3 4. If you multiply this 2 3 4, you again get 2 3 4. Isn't this 2 3 4 is also eigenvector? Right? This 2 3 4 also seems to be eigenvector. You multiply anything. You multiply 0 1 0. I mean, this is the identity matrix. Let's suppose minus 1 2 3. You multiply this, you will be getting minus 1 2 3. Isn't this minus 1 2 3 is also eigenvector? Because you are getting the same vector and the corresponding lambda is 1 here, right? So for lambda equal to 1, it seems that everything is eigenvector. Is this possible? That there are infinitely eigenvectors for this matrix, identity matrix. So can I say that there are infinitely many eigenvectors for identity matrix A? Can I say something like this? Identity matrix I or A does not matter. Let me know. What do you think? See, it seems like, right? You take any vector, it's an eigenvector. So what do you think? Answer is yes or no, or we are doing something wrong? So let's just answer this particular question in the next video. Okay, so just let me know in the comment that what you think. Is there anything fishy here, or this is the correct statement? Let me know. This is true or false. Okay, so just let me know that what do you think about this particular statement. Okay, and then we will see in the next video. Thank you.